In this problem, we have a driver in a 1,000 kilogram car traveling at 20 meters per second who suddenly slams the brakes and skids to a stop. We'd like to calculate the length of the skid marks and hence the stopping distance of the car. We'll start off by drawing a free body diagram of the car, and we're going to represent the car as a point particle that's on a surface. Now, since the car can't accelerate downward through the surface, we'll say that the acceleration perpendicular to the surface, perpendicular to the road, is 0 meters per second squared. So that's the acceleration in the downward direction. Since there's a surface in the way, the car can't accelerate down through the surface. So let's think about the forces that are acting on the car. So we have gravity, which is always directed downward. And the force of gravity, or the weight of the car, can be calculated by multiplying the mass of the car and the free fall acceleration. Hence, the force of gravity will be 1,000 kilograms times negative 9.8 meters per second squared. And this is going to give me a weight, or gravitational force, of negative 9,800 newtons. So we also have the normal force from the road. So the road is going to push up on the car, supporting the weight of the car, preventing the car from accelerating downward through the surface. And that's what we call the normal force. Now, since the tires leave skid marks on the road, we can assume that the tires have transitioned to kinetic friction and are sliding on the road. Hence, there's a kinetic friction force acting on the car, which is always in the opposite direction of the movement. So if we assume the car is traveling towards the right, then the kinetic friction force will be opposite to that, which is towards the left. Now, if we apply Newton's second law in the y direction, we have the summation of all the forces in the y direction is equal to mass times acceleration in the y direction. Now, since there's a road in the way, we have the constraint that the car can't accelerate perpendicular to the road or in the y direction. So if we substitute 0 for our acceleration on the right side, we see that the right-hand side of the equation ends up being 0. So we have the summation of all the forces in the y direction is equal to 0. So if we add up all the forces in the y direction, namely the normal force from the road and gravity, we should end up getting 0. So we have the normal force plus gravity. And remember, that force is negative because it's pointing in the downward direction. And that should equal 0. So then we have that the normal force is equal to 9,800 newtons. And remember, the normal force is just the amount of force that the car exerts on the road and vice versa due to Newton's third law. This is also the amount of force that the road puts on the car in the upward direction. So in a sense, you can think of the normal force as representing how hard the car is pressing on the road. Now, we'll need this quantity in order to calculate the amount of kinetic friction between the tires and the road. So let's calculate the total amount of kinetic friction between the tires and the road. So we have the kinetic friction force equals the coefficient of kinetic friction multiplied by the normal force. Now, this equation implies that the total amount of kinetic friction force between the tires and the road will be proportional to the normal force, which is representative of how hard the car is pressing on the road. So the harder the car presses on the road, the more kinetic friction force there will be between the tires and the road. That total amount of kinetic friction force is also dependent on this coefficient of kinetic friction, which of course always depends on both materials that are in contact, which in this case we have the tire tread and the road itself. So since they gave us the coefficient of kinetic friction between the tires and the road, we can go ahead and calculate this kinetic friction force. And this is the total kinetic friction force between the road and all four tires. So we have 0.8, the coefficient of kinetic friction between the tires and the road. which is a unitless quantity, and then we'll multiply that by the normal force, 9,800 newtons. So this gives us 7,840 newtons. And that's the total kinetic friction force between the tires and the road. So since kinetic friction is the only force acting in the x direction, we can go ahead and calculate the acceleration in that direction. So if we apply Newton's second law in the x direction, we have the summation of all the forces in the x direction equals mass times acceleration in the x. So since kinetic friction is acting towards the left, we'll go ahead and make that negative. So negative 7,840 newtons equals the mass of the car, which is 1,000 kilograms, multiplied by the acceleration parallel to the road, or in the x direction. If we go ahead and divide by 1,000, we end up with an acceleration parallel to the road of negative 7.84 meters per second squared. Now we know the car is decelerating mathematically from the fact that the acceleration is negative and the velocity is positive. Anytime the acceleration and the velocity have opposite signs, the object will decelerate. In other words, whenever the acceleration and the velocity vectors are in opposite directions, the object decelerates. So in this case, since the car was moving towards the right with a positive velocity and its acceleration is negative, the car is slowing down. So now that we have the acceleration in the x direction, we can make use of one of the kinematics formulas to calculate the length of the skid marks, or the stopping distance. So we could make use of this kinematics formula. V final squared is V initial squared plus 2 times the acceleration times the displacement in the x direction. We know that the car will eventually stop, so its final velocity will be 0. And the initial velocity of the car was given in the problem. Before the driver slammed the brakes, the velocity of the car was 20 meters per second. So we have 0 squared, which is still 0, equals 20 meters per second squared plus 2 times the acceleration rate, which was negative, which we found with Newton's second law, negative 7.84 meters per second squared, multiplied by the displacement of the car in the x direction. So this is the distance that the car will travel in the x direction before it comes to a complete stop, before its final velocity is 0 meters per second, given that the starting velocity of the car was 20 meters per second. Now we can go ahead and solve this equation. So we have 0 is equal to 400. I'll leave the units out here, but I'll include units in the final answer. Minus 15.68, which is 2 times 7.84, and then multiplied by the displacement of the car in the x direction. I'm going to go ahead and add the negative 15.68 times delta x over to the left side. So I have positive 15.68 delta x, and that's going to equal 400. And then last but not least, I'll go ahead and divide by 15.68. So that's going to leave me with the stopping distance of the car, or the length of the skid mark, which will be 25.5 meters.